Welcome to the PolariQon room temperature desktop quantum computer demo. Today what we're going to do is walk you through our platform, and what you're looking at here is our kind of home screen, our home dashboard, and we're going to walk you through a number of different applications, give you kind of a behind the scenes tour of some of the calibration tabs and the logs, and some of the speed comparison metrics and things like that are probably a little bit more for the engineering community, but at least give a good perspective on the quantum infrastructure itself. Most of the quantum industry is solving the wrong problem. Everyone is racing against physics, and each approach pays a different tax. Superconducting machines like IBM and Google chill qubits to near absolute zero in refrigerators the size of a room and data center. Trapped ion neutral atom systems hold individual atoms in ultra-high vacuum chambers steered by racks of precisely tuned lasers. Photonic systems demand near-perfect optical alignment where the smallest drift breaks the computation. Different apparatus, same story. Bulky, lab-bound infrastructure that scales into tens of millions per machine. Scaling means building more of that infrastructure at tens of millions of dollars per machine. Here at PolariQon, we are taking a very different path. Our platform today runs 44 logical error-corrected qubits, stable and entangled at room temperature on a desktop. And those qubits work as one unified system, not as fragile pieces sitting near each other, which is what actually gives a quantum computer its power. Here's why that changes everything. If it validates externally, the hard part of quantum computing is already done. What is left isn't physics, it's engineering, shrinking control electronics into a chip, the kind of thing semiconductor industry has been doing for decades and tens of thousands of times. Everyone else is still fighting the infrastructure war. We've moved the contest to silicon, a war the industry already knows how to win. So let's start with what you're looking at here. This is the kind of home screen. It's our oscilloscope screen. You'll see the four traces here, the four different channels, four different traces. These are reference levels. Okay, I'm going to go ahead and run a quick calibration on this, just to make sure that the system is calibrated. Now, why do we do this? Why do I have to run a calibration? In traditional classical computing, like your laptop, desktop, GPUs, CPUs, the whole world, the whole universe of transistor-based logic gates and circuits, they are electrical systems, and everything references to ground. In a quantum computer, these are live physical entities, and they don't have a ground reference. So you have to find that reference. And when you're running your computations, you're running your algorithms, you're building your circuits, you're building your gates, you need to constantly refresh what that reference point is, because this is a physical system. Things drift, charge accumulates, and so you need to account for that. So we run a calibration, and we get to a point where we have a stable system. How do we know we have a stable system? Well, for example, at the bottom here where you look at coherence and fidelity, that's gate fidelity and our coherence. Our coherence is not, as close, you want to be as close to 100% as you can be. Your gate fidelity, as much as you can be. You want your T1 and T2 times to be as long as possible. As you see this, we're in the seconds to thousands of seconds of T1 and T2 time. That's seconds. The industry is battling just to get T1 and T2 times into the milliseconds. They're dealing with microsecond coherence. Why is that? It's fundamentally the nature of our qubit. Our qubits are basically what is called a polariton. It's a quasi-particle. It's a marriage between material and light. What that means is there is a physical aspect and then a photonic aspect, and the marriage between the two, when they come together, and into a polariton, that quasi-particle um, exists, and it exists as well in what is called a Bose-Einstein condensate. I won't get too technical, but essentially think of it as a cloud of these polaritons. So it becomes very stable, and that gives us our stability and our coherence. And there are ways to engineer the design of the environment for these polaritons to maintain stability and to, in a sense, re-energize them continuously so that they don't decohere. And that's really the core backbone of the technology behind our quantum computer, which is why this is going to be stunning, and it will create an upheaval in the industry that has really not been seen to date. Now, the state is read out using a capacitive weak measurement, right? So these qubits, they sit in a 0 or a 1 state or some angle, and you measure that. And basically, the sensor produces an analog voltage that tracks where the measured state sits relative to that 0 and 1 reference rail. That's why you see the active channel doing the work in the millivolts, zeros and ones, and then you have the traces that sit flat as baseline. So below the plot, you've got the live channel voltages. You'll see in there, and then you also have as I mentioned, the coherence and the fidelity and so forth. BE temperature. What's our temperature? It's 295 degrees Kelvin. In case you don't know, that's pretty much room temperature. Okay. There's a phase drift. That's one to watch. You watch your phase drift because over the course of a session, as the condensate's resonant detuning drifts slightly, the phase accumulated per gate drifts with it, which is what the calibration itself corrects. So this is just some background. I know it's somewhat technical, but it's really important to understand that when you're dealing with a quantum computer, you're not dealing with a traditional classic computer. Already ran the calibration. This is where you can go run the calibration. You can also run an adaptive calibration. This is where we kind of tie a target to the Bell state and to the Bernstein-Vazirani test to be able to make sure that we are constantly, tuning this to meet those different KPIs. We will run through the Bell state and the BV Bernstein-Vazirani sweep shortly, so I won't get into that here. But we suffice it to say we can run an adaptive calibration as well. We do have a screen here. It's just a speed comparison. This is just to give a sense as to the speed of quantum when it's running through gates compared to the speed of a classical computer. Now, how do you do that, right? Well, just as in you have AND gates, OR gates, NAND gates, and NOR gates in classical computing. These are the fundamental building blocks of every classical computation for, again, all computing to date. They're built from transistors. There are transit times for these gates to operate, and you can measure and calculate those. And you know that if I run, through 1,000 gates and they're a microsecond or whatever it is per gate, I know that if I've run 1,000 of those, I've got a millisecond of time, right? So that you can calculate that based on and estimate that based on time. Similarly, quantum computing has gates, not the traditional AND gate, NOR gate, and NOR gate, but you have Hadamard gates, you have XOR gates, you have CNOT. So you have different types of gates, and so when you run through a quantum circuit, you also can calculate that time. So running the speed test, when I click on that, what you're going to see is you're going to get a timing histogram here. And essentially, if you look at the bottom, you'll see that, okay, for a given number of trials, 100 trials as an example, it took 12 milliseconds, whereas for us it took 1/10 of a millisecond. So basically we were 122 times faster. If I change this as an example here to 1,000, run that speed comparison 1,000 times, or over 1,000 times the number of gates and so forth. And you can see the trial time running there. Boom, you see it. Similar thing, or 112 times faster, right? So that just shows the relative speed. The last geeky thing here, we do have a log, so you can actually see the logs for the different activities that we're running. And so that's kind of your engineering tab up in here. And now we're going to go to what you care about here as a customer, right? What are the types of applications and things that a quantum computer can actually do? I am treating the Bell State test as its own application just because it is the gold standard in quantum computing to demonstrate quantumness and how a computer is truly doing quantum computing and there's no hidden classical effect behind it. So here we run that Bell State test, and what you want is I won't get into all the geeky math of all the different angles and so forth that you're calculating and taking sines and cosines and so forth. But the bottom line is when you run the circuit, you want a result that's greater than 2. And so and you get that result by adding these 4 numbers up over here, these E values, and we run it at basically at 45 degrees, 135 degrees, 45, 135 degrees again. And the importance of that is if it is 2 or less, it's classical, right? But if it's greater than 2, you can only get a number greater than 2 if you're running a quantum computer. So as you can see, we ran it, it's 2.89. There is a circuit here in the middle that shows you the circuit because that's typical way to run a Bell State test through your 2, they call them Alice and Bob. It's very, very, very classic in the industry. These 2 qubits, and they're correlated via entanglement. So that's the Bell State test. I won't spend much more time on that. We'll move quickly to the Q password. And again, this is just to demonstrate. We're not breaking, some world record here in encryption or anything like that. It's just to demonstrate that we can run a classic quantum algorithm. So I'll just I'm going to put a word in there that I want to encrypt, and then the quantum computer is actually going to decrypt it. And again, we have 44 working logical qubits here, and so that's what does the work. It builds the different gates, and it solves through interference and decrypts the passcode. So, for example, I put in, I'll just put in Popeye likes spinach as a password. I'll just go ahead and show that here. And so I encrypt it, and when I encrypt it, you're going to see that Popeye like spinach is going to come up with a hex code right here. So here's your hex encrypted value, and then the 44 logical qubit angled state. And now when I run the decryption, it's going to reveal it. You'll look over here, and boom, just like that, Popeye likes spinach. And that's the basically a demonstration of the gate operations that we're running different gates, and we can execute a quantum program and a quantum algorithm on our quantum computer. Again, this is about circuit building. It's not about cryptographic security. Some great claim there. The transformation is an XOR with a key, a classical cipher running on quantum hardware. The angle state that you see displays shows the per qubit encoding, 1 angle per qubit, which is the right way to read this demo. The full description of an entangled state involves the larger 2 to the 44th power Hilbert space. So let's go to the BV sweep. This is interesting. I kind of referenced that back under the calibration because we target a score on that for what's called the Hamming distance score, HD score of 0. It's just like on the Bell State, we targeted a value that's above 2 when we're doing the adaptive calibration. And the BV sweep, what we basically do, we have a string here. It's a secret string, okay? And this secret string, we're going to basically run a decode, and we're going to check it each bit. Okay, now what this actually means is we're going to recover that hidden bit string. And in quantum, you can do this in one query because of entanglement. You can actually look at all of the states at one time and in one shot get the number. Whereas in classical, you have to look at each bit separately. So it requires, in this case, if there's 44 bits, we have 44 qubits. It would take 44 different shots to do this, right? So we're going to go ahead and run the BV, and you see, actually what I'll do, let me just hit the random a few times, change the numbers in here. So to refresh that, we're going to run the BV, and what you're going to find, the Hamming distance over here is 44, and it's going to build until it solves this problem and gets down to a 0, which means that every bit that it's basically recovering over here in this row with the red and the green bits, you'll see that over a period of time here, as this runs, it's going to basically recover all the bits in this string. And it's going to do it here. Right now it's on round 2, round 3, round 4. In round 3, it basically recovered all the bits. And we used 134 gates to do that. So you can see takes a little bit of time and demonstrates, that basically BEV will converge to an HD of 0. So in a sense, these are applications that you can run, password, BV sweep. We're going to get a little bit more sophisticated here and look at a crypto walkthrough. This tab runs cryptography demonstrations. We have kind of 3 different scenarios. We have the SHA-256 hash, the parameters password set to 16, okay, and the prefix length is 4, and or we can run an AES Grover, or we can run the RSA period finding. Okay, so in this case, the RSA bits are 16, the period is 200. So what we're going to do is we're going to read the results, the result panels left to right, okay, and you'll see the different number of classical operations it would take, and then the quantum operations that it would take. So let's just start with an RSA period finding, okay, and what you're going to see here is the operation count advancing, all right, and as the operation count advances, you'll see the results. In this particular case, we factored 53,357 into 229 times 233. So we basically ran that. It took 230 classical operations, 200 quantum operations. Doesn't seem like a big deal. Same thing with the time. It actually takes us more time because of the overhead of quantum. What would happen over a large number, not just 16 bits, but when you get into something like an AES 128, then all of a sudden the quantum is going to far surpass the ability of a classical computer to decrypt. So we'll run an AES Grover search. We'll run that. Grover 17 iterations versus 410 classical. So when we run a Grover search, again, we're actually much fewer operations. And again, over time, you can even see here, that is a 1, we're 9 times faster. If we run it again, let's see if anything actually changes. We're about 17 times faster over time. And then if we run the SHA, I'm going from the end to the back to the front here, but we'll run the 0 collisions found, classical operations 4,000 to run that, only 16 operations for us. So we measured the advantage at the algorithm level. The quantum speed up lives in how the operation count grows with size. So in quantum, the operation count grows based on the square root of n, not in any single run. Is it faster? The scaling holds regardless of this is a toy problem with here. Now we'll get to Shor. Shor's is an interesting one. Shor's has got a lot of attention because the whole world's worried about post-quantum decryption. And, there's an entire industry now built around post-quantum cryptography. And the question is, when is RSA 2048, encryption, which is the backbone of a lot of the encryption on the internet and everything else, going to be broken? Well, there are estimates out there that if you run Shor's algorithm and you have 4,000 logical qubits that are error corrected, you can break RSA 2048. Well, we can't break RSA-24A because we only have 44 qubits. Now, we will be able to scale into the thousands pretty quickly because of the fact that our work that has to be done now is just tried and true, industry known, integrated circuit control plane work. We just basically have to be able to control our qubits that are roughly 1,500 on a chip today. We can only access a handful per chip, which is why out of those 1,500 we are only running 44. Once we shrink wrap our control logic or our control plane and our taps into an integrated circuit size, we'll be able to actually control and read hundreds of qubits per chip, and so it will be no time at all for us to get to a number that can break Shor's algorithm much more quickly than the industry is currently projecting. So to run Shor's, we can, for example, I can take a 10-digit number here. Okay, there's a 10-digit number. I can take let's do a 14-digit number, and let's say I want to factor that into two 7-digit numbers, right? Something close to that. And the reason you pick this complexity is, if you want to do 3 digits or 5-digit numbers or 9-digit numbers, is just to show the level of difficulty, right? If I have an even number, for example, I can just divide by 2 and I can get 2 factors. That's very unimpressive. But to do this this kind of a number here and into 7 digits, that means I need to find 2 7-digit numbers you multiply to get that. So let me go ahead and run Shor's algorithm. Well, this is running. I'll tell you a little story. It was interesting. We had a little bit of an exchange with Google Gemini. We asked our PolariQon, quantum computer system to factor a series of 14-digit numbers that Gemini supplied us. And Google's LLM claimed that it knew the factors each time our system returned a different valid factor pair. And each time Gemini checked the math and conceded that our factorization was correct and that its own was wrong. Very interesting. We did this 4 different times, 4 different rounds. The system every time returned a mathematically valid factorization of every number it was given. And Gemini each time had to basically, say, yes, you are actually correct. Look at this. Here we are. There's two 7-digit numbers we multiplied together to get the n number, right? Pretty impressive, right? And we did that down below here, the PolariQon quantum in 44 seconds. A regular computer could, do this, in a trial, division, can do this, much faster. But the challenge is scale, right? The challenge is as you scale this up into, much larger numbers, that you're not going to be able to. A classical computer can't even break it, right? Whereas a quantum computer can, given enough bits or qubits. So let's see here. Of course, you could verify this. I could take the 2 digits and put them in here and get the PQR. So we're going to move on. Next tab is the AES decryption. I can basically type and generate a password here. And what we're going to do is we're not going to do AES 128 decryption. So we're not going to decrypt 128 digits. We're going to only decrypt the last 16 bits. But we're going to use the format of AES and to encrypt. And then we have a known, let's call it prefix. So it allows us to basically build out a string for 128 digits and decode it, basically demonstrating, today with 44 qubits, we could do the last 16 or the last 24, okay, depending on how many search bits we want to have, okay. So right now we just have a PolariQon 2026 exclamation point. I'll put some numbers in there as well. And let's go ahead and let's see here. If I click on 8, I can click on 16, or I can click on 24. I'll just stick with 16. we'll do a one-click demo. And now it's encrypting, it's searching. Now it's trying to basically decrypt this plain text, and there it is down there. And it decrypted it. And what's, you'll see the results, which you'll also see down here, to the key search space was 2 to the 16th power. If I click on 24, I do the same thing. I'm going to have, once it's, there we go. So PolariQon reveal plain text, boom, there it is. The search space again is 2 to the 16th power. It took 201 Grover iterations to get that done. The classical time again is going to be, in this case, it was actually much longer than it took us, and we were 9 times faster. And the key was recovered, and that's our result. The next screen, it's interesting. It's kind of a medical, and it shows how you can encode brainwave activity. We're going to upload a live brain EEG signal into this, and just basically how you can encode the data from the raw input data into qubits. And this is valuable when you want to run things like disease detection and so forth. We've actually done some of this and showed it to a physician who was very interested in this. Today we're doing this again with 44 qubits, but the whole point of this is just to show you how we are encoding the data into the qubit. So the 44 logical qubit angle vectors are below, and the different colors represent the different lines you see above. And so that's just a simple example of how we can encode data. The last is what we call bring your own program, BYOP, almost as good as BYOD. BYOB, but you essentially have a scenario here where we'll create 4 different cities, and there's a cost associated with traveling from city A to B and B to C and C to D and A to C and A to D and so forth. You basically can envision a 4x4 grid with different costs, and the idea is for the quantum computer to identify the shortest or lowest cost route to take. So it's very basic. It's nothing that's going to be too complicated. Obviously, this is just to demonstrate the capability to do this. So I'm going to go ahead and paste the OpenQASM code in here. So you basically, come into the OpenQASM 2.0 space over here. I'll do Control V to paste it. And what you're going to see very quickly is we're all of the gates down at the bottom here. So very cool. Here's our circuits, all of our gates, and what you're seeing here is the circuit. This is actually considered a deep circuit. A lot of platforms might have, for example, market themselves as having a lot of qubits, but they don't have the ability to do what's called a deep circuit algorithm. So you'll see in our case here, we have dozens of gates, and this is considered a deep circuit algorithm. So go ahead and just kind of roll down to the end here, just so you can see there's the actual circuit, and then up at the top I'm going to say run on hardware. And so what we're going to do is we're going to let this run, and I'll hit that, and what you are going to notice over here, here's our calibration is ready. It's starting the execution. So we just started with our first shot. So this is going to take a little bit of time to run, and we'll let this do its thing. So right now it's executing the different circuits. It's running its iterations. So we're going to run 50 shots or 50 iterations here, and you also notice we're maintaining our calibration through this process. So what I'm going to do, because this does take a little bit of time, I'll come back in just a bit and we will update as we go. Okay, as you can see, we're progressing a little bit here. We have an output histogram that's building. We're on step 21 of 50, or iteration 21 of 50. So just wanted to update you on the progress. Also, you can see up here in the upper right, is it determined that the path was B to C to D to A back to B as the valid and lowest cost path. We did this in 50 shots, and you can also see the actual probability is 100% that this is the best path to take for our optimization problem. So again, the whole point of this is just to show you an optimization problem, 336 gates. If you have an optimization problem, you want to bring it, we'd love to work with you and show you how our platform can execute.